So, good morning, students, and happy new year to everyone. So, recording is started. So, this is a class of geotechnical engineering. So, we are discussing about module 2, part 2, that is CPS analysis of water through hydraulic structure, you can say. Okay. So, in the last class, we have discussed um, Laplace equation of two-dimensional flow, then stream function, velocity potential, and also a little about flow net. Okay, so what is the definition of flow net? It is an imaginary line and it's made up of flow line and equipotential line join or act mutually perpendicular to each other, and it is used to study the CPS of water, or you can say to study the CPS analysis, and it is very useful for CPS analysis. Okay, so today we'll discuss about the application of flow net, how flow net is used for CPS analysis. Fine. So let me first share my screen. Okay. So I hope my screen is visible to you. The stream function is already discussed with you. And about flow net, it is also, I guess, it is already discussed with you in the last class anyway. So this is the schematic diagram, you can say, a line diagram of a flow net. Okay. If the flow is in this direction, the line parallel to the direction of the flow is termed a streamline or flow line. The line perpendicular to the streamline as well as perpendicular to the flow direction of the flow, they are known as equipotential line. And equipotential line are drawn in such a way that they have a equally potentially drop. Okay, equal potential drop may should be exist between these two successive equipotential line. Okay, so here next, I guess this also discussed that properties of flow net. Let's discuss again one more time. So what are the properties of flow net? The first property is what? The flow lines and equipotential lines meet at right angles to one another. If you can imagine the flow net diagram, they are mutually perpendicular, isn't it? The equipotential line and flow lines are mutually perpendicular to each other. That means they make or they meet at right angles. Okay, and a field are approximately square so that a circle can be drawn touching all the four sides of the circle, or four sides of the square, sorry. So what is the field? The portion enclosed between two successive equipotential line and two successive flow lines. That portion is known as field. Okay, and the field, the significance of field is what? The fields are approximately square. Approximately, they are considered as square in such a way that you can draw a circle within a field touching all the four sides of the square. Okay. Next, third property is what? The quantity of water flowing through each flow channel is the same. Now, what is the flow channel? The portion enclosed between two successive flow lines. If you can remember the diagram. Okay. The portion enclosed between two successive flow lines is known as flow channel. The water is flowing through that particular channel. Okay. Now, if I go to that previous drawing here, let's see here. So this is a flow channel. One here in this particular drawing, how many flow channels are here? It's showing. It is here three flow channels are showing. One, 2 and 3 flow channel, and this particular area is enclosed between two streamlines 1 and 2, okay, successive streamlines, and this is the field. All blocks are known as field. Okay. Okay, so quantity of water flowing through each flow channel is the same, and also have the equal potential drop exists in a flow net. It is the third property. Okay. Okay, wait. Yeah. So fourth property is what? And fourth property is, if smaller the dimension of the field, greater will be the hydraulic gradient and velocity of the flow. So if you squeeze the dimension, that is, if you shrink that no, the field area, if area is small, the velocity will of course will going to be increased to maintain the value of q. Okay, since q not, the amount of water is flowing in particular flow channel is not changing. So if the dimension of the field is changing, that means the velocity is going to be increased, as well as the hydraulic gradient also be going to be increased if the dimension of the field is going to be decreased. Okay, fine, they are inversely proportional. Fine. So next we'll discuss about application of flow net. So mainly application of flow nets are, so a flow net can be utilized for the following purposes. Here you can see determination of CPs, determination of hydrostatic pressure, determination of CPS pressure, and determination of exit gradient. Okay. Okay, fine. So you have to remember this for application of flow net. Okay, so we'll discuss about the main part, that is the determination of CPs in this class. Okay, that means the flow net is used, or flow net is applicable to study the amount of water flowing through the dam structure as CPs. So we can determine the amount of water. Okay, so how can we determine the amount of water? Let's discuss in this class. So there is a derivation of a particular formula. So for that, so let's discuss about determination of CPs using flow net. Determination of CPs using flow net. For that, you have to draw this particular flow net. It's a schematic diagram of flow net. Say 3 flow channels are there. You can randomly you can give, or 4, 5, 6, whatever. N numbers of flow channel will be there. Okay, or N numbers of potential drop will be there. Okay, you cannot decide. Okay, here for now. Say N numbers of potential drops are there, and N numbers of flow channels are here. Okay, and a field having length L and width B, say, and delta Q is the amount of water flowing through each channel. So here like that. Okay, so in the given figure shows the portion of the field portion of a flow net. Okay, this is, and the portion between the two successive flow lines is known as flow channel. Yeah, it is already discussed here. This is our flow channel, and the portion enclosed between two successive equipotential line and successive flow lines is known as field. So these all are termed as field. The boxes are termed as field. Okay. 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 So if you can remember that particular drawing that we already discussed here, let's proceed to that derivation. Okay. 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 So here let B and L be the width and length of the field that already discussed in the diagram. B considered as a width, L is considered as a length of the field. Okay. Delta H is considered as a potential drop, or you can say head drop through the field. That means for individual field, or individual field having a potential drop of delta H. Okay, all boxes or all field having a potential drop of delta H. Okay, delta small h. Delta Q is the discharge passing through each flow channel. Okay. And if you consider capital H is the total hydraulic head causing flow. Okay, which is the difference between upstream and downstream head. If you consider a dam, okay, the water is flowing from upstream to downstream. So there must be some potential head drop or hydraulic head drop. Say that head drop is say capital H, and this capital H is divided in n numbers of potential drop between two potential line with a potential drop of delta H. Delta H is the potential drop through individual field. Okay, that means we can say if there is a n numbers of potential drop, okay, n small n numbers of potential drop, that means delta H multiply small n, we can find out capital H. Okay, same thing. Okay, that means capital H is divided in n numbers having each field a potential drop of delta H. Okay, these are some nomenclature you have to write or you have to know these things. Next, from Darcy's law of flow through soil. As per Darcy's law, you know that what? As per Darcy's law, you know that. Hello? Hey, class sudah sudah. Class ko di sudah. Tolotnya sudah dong, class ko di. Mau luain ya, luain ya. Okay. So as per Darcy's law, you know that Q is equal to KIA. So in this particular, for this derivation, Q is replaced by delta Q. Since we are first, we'll find out delta Q for individual flow channel. Okay. Delta Q is what? Your discharge passing through each flow channel. So delta Q, you can also write KIA as per Darcy's law, where K is, you can remain as K only. Okay, for one direction, K will be same. Hydraulic gradient, I will be, you know, I is equal to H by L. That is hydraulic drop divided by length traveled by the water. In this case, H will be replaced by delta H, since we are talking about one individual flow channel having a field, or for which field potential drop is delta H for each field. So delta H by L. L is what? L is your length of the field. That means water is flowing along the length, right? So we have to put the length traveled by water as L. K into delta H by L multiply now cross-sectional area. Now since we know it is a two-dimensional diagram, if you remember that line diagram, the cross-sectional width is taken as unit. Okay, the thickness of the line is considered as unit, and the width of the field is what? B. So B into 1 will be your cross-sectional area. Okay, B into 1 will be your cross-sectional area with respect to the flow of the water or seepage of the water. Okay, the area perpendicular to the flow water is taken as a cross-sectional area. So here cross-sectional area is B into 1. 1 is your thickness of the field. Okay, considering unit thickness. So this is the amount of water flowing through a particular field, particular flow channel. Okay, one flow channel. Now here, if you consider ND as the total numbers of potential drop in the complete flow net for a particular one flow channel, that means along the horizontal direction. If you consider ND is the what? N for number, D for drop. Okay, so total number of potential drop in the complete flow net. So you can find out it's equal to H by delta H. Okay, that we already discussed that if you see indirectly, capital H will be what? Individual potential drop multiply the numbers of drop, isn't it? Total drop equal to what? Individual drop multiply the numbers of drop. So capital H equal to delta H multiply by ND. ND is what? Your numbers of drop in a complete flow net. Okay. So from this we can find out delta H, which is the individual potential drop, can be found out by total hydraulic head divided by ND. Okay. So H by ND, it's very simple to understand. Individual potential drop within a field will be equal to total head loss by ND. Okay, fine. So by putting delta H, the value of delta H in the Darcy's equation, that is delta Q, so you will find delta Q equal to K into, in place of delta H, put capital H by ND, capital H by ND, multiply B divided by L. Here you can see B divided by L. So delta Q is equal to K into H by ND into B by L. Okay, so this is the amount of water flowing through one flow channel. Okay, there is just for a particular single flow channel, this is the amount of water flowing. Okay, now if you know the total numbers of flow channel, you can easily find out the total discharge through the whole flow net by just multiplying the discharge through individual flow channel multiply by the numbers of flow channel. Okay, so for that, let's assume NF is defined as the total numbers of flow channel in the flow net, and for number F for flow. Okay, so NF represents numbers of flow channel. Now it is now very easy to find out total discharge through the complete flow net. How can you find out? Q is equal to summation of delta Q, that is Q, delta Q is for whole flow channel. You have to just sum it up, you will find out the total Q. Fine. How can you find out mathematically? Delta Q multiply by NF. NF is your total numbers of flow channel. So just fill up the value here. Delta Q is what? K into H by ND B by L into NF. Simplifying the equation, Q is equal to KH NF by ND B by L. Okay, this is the equation for discharge through a dam or through any hydraulic structure which passes through as a seapiece. Okay, now as per the property of flow net, we know a field is considered as a approximately square. You know these things, right? So as per the property of flow net, the dimension of field is considered as approximately square. For that square field, assuming square field, we can consider B is equal to L, isn't it? So for a square field, assuming a square field, B can be equal to L, so this term will be cancelled out. So finally, for square field, usually for flow net, the general equation of discharge is defined as Q is equal to KH NF by NT. So you have to remember this term also. Okay, and it's very important. It's wait. Where it is? Yeah. So for square field, B is equal to L. So Q is equal to the final total discharge through a dam structure or hydraulic structure which come as a seepage. The total seepage will be KH NF by ND. Okay, this equation is very important for exam purpose and even for a competitive exam. Many GATE, even in a GATE exam also, problem must come related to this equation. Okay, it's very important. So Q is equal to KH NF by ND, where NF is your numbers of flow channel, ND is your numbers of potential drop, K is your coefficient of permeability, H is your hydraulic head. Okay, total hydraulic head. Fine. And this is for isotropic soil only, it's applicable. K. Okay. So this is your application of seepage. Now, as I already told you, this flow net is used for determining seepage of water through dam. So here you can see this is a line diagram of a dam. It is very easy to understand now how flow net is used for seepage analysis. Okay, so here you can see it is a very simple line diagram of a dam. This is a upstream phase, this is a downstream phase, isn't it? This is a water is storage here. This is a full reservoir level. Okay, this is the maximum water level here. This is amount is known as freeboard. This is crest weight. Okay, and water is rested on the upstream phase, and this because of this weight of the water, it creates some pressure on the upstream phase of the dam, isn't it? So this water will try to seep through the dam structure and it will go like this. Okay, and the pattern, the flow of water, which is known as seepage of water, is studied by comparing the flow water with a flow net. So here you can see this is the flow net, which is an imaginary line which are drawn, okay, to study the flow net. Here you can see this is the along the flow direction, they are known as flow lines, and the lines perpendicular to the flow lines are equipotential line. And this equipotential line also parallel to this upstream face of the dam. Okay, these flow lines are parallel to the upstream face of the dam. Okay, so in some competitive exam, this also asks this the flow line, sorry, the upstream face of the dam. You have to remember the upstream face of the dam. It is also considered as equipotential line, since all other equipotential lines are parallel to the upstream face of the dam. Okay, and the topmost flow lines, the topmost flow line. This is top line, na? Above this there is no flow. This is the maximum flow line. Above the top flow line there is no water. So this top flow line is known as phreatic line. Okay, this is the significance of this. So what is phreatic line? Phreatic lines are the top flow line and which is defined as the line within a dam section below which there are a positive hydrostatic pressure exists in a dam. Okay, so below this there is a positive hydrostatic pressure will be there. Above this atmospheric pressure will be there. Okay, and here one component of dam is showing here. It is known as filter. Okay, why this particular filter is provided here? To divert the flow lines. That means if flow net this filter is not provided in the downstream phase of the dam, what will happen? This flow will go and cross the downstream phase. Okay, it will cross the downstream phase, and if the flow or if the seepage cross the downstream phase, okay, it will may collapse the dam structure. So to divert the flow from the downstream phase, one filter is constructed. Filter is made up of coarse grained soil, okay, or coarse aggregate, you can say. That means a particular material having more voids, okay, and water get attracted towards this particular section, and it will simply divert the direction of the flow and it will pass through this filter portion only. By this, we can safeguard the downstream phase of the dam. Okay, so here you can see all are, you know, concentrated on the filter section only, and they are equipotential line. Okay, so this diagram is very easy to it will be helpful for understand the flow net. Okay, so this is all about today class. Next class we'll do one problem on related to flow net. Okay, fine. That this is all about today class. So here I just want to stop my sharing. Okay, is it clear? Okay, then I'll not wait further. Then I just first let take your attendance now. Before it, I just want to stop my recording here.